Good day, guys. We talked about categories of colligative properties in our last class, but we didn't read them. So we'll be dealing with them one by one. The first one we'll talk about today is the lowering of the vapor pressure. Under the lowering of vapor pressure, there are some certain things that need to be considered. That is mole fraction and molality. Now you see the mole fraction, which is represented with X, of a component is the ratio of the molar amount, that's the mole of the particular component itself, then to the total numbers of moles of all the solution that are present in it. That means that adding each and every constant of the mole respectively. That is what we call mole fraction. Molality is a concentration unit defined as the ratio of moles of solute to the mass of the solvent in kilogram. Please be very careful while using all these formulas. Whatever is being given is what you should obey. We have number of mole being equals to mass over molar mass when dealing with some questions. Or you can call it weight over molar mass. It's still the same thing, but it is very much more okay to use weight over molar mass. And also it is not molarity, it is molality, because molality tends not to be affected by temperature, which is mainly what we need more. Let's take some examples under mole fraction and molality. It says that the antifreeze in automobiles radiators is a mixture of equal volume of ethylene glycol and water with minor amount of other additives to prevent corrosion. The question asks, what are the mole fraction of ethylene glycol? And we know that to find the mole fraction, we've given you a formula for that. What is the molality of ethylene glycol in a solution prepared from 2.22 times 10 raised to power 3 gram of ethylene glycol and 2.00 times 10 raised to power 3 gram of water? From our formula, it was instructed that we need to find the mole of each of the constituents, that is the ethylene glycol and the water. So from our formula, we need to find the molar mass of ethylene glycol and the molar mass of water, and also then finding the mole, we know it to be equals to mass over molar mass. The formula I gave you guys at that time, this would be in gram. That's the mass for this would be in gram. And from there, we know our mass is 2.00 times 10 raised to power 3 gram. Converting it to normal values from its standard form, you have 2000 for water and 2220 for the mass of ethylene glycol. From there, our molar mass for ethylene glycol is 62 gram per mole. Molar mass of water is 18 gram per mole, and our mole would be for ethylene glycol is 35.8 mole, while the mole for water is 111.1 mole. And from our A now, our mole fraction was asked for ethylene glycol, not water. So that will be the mole of ethylene glycol itself over the addition of all the mole. And that will be 35.8 over the addition, which will give us 0.244. Then our molality now would be equals to, like I said, the solvent is water. Do not forget. So it will be the mole of the solute being given, which is ethylene glycol, and over the solvent. And the solvent has to be in kilogram, like I told you guys. So that will be 2000 divided by what? 1000, which will be equals to 2. And our answer would give us 17.8. We also have converting mole fraction and molar concentration. Now you can be asked to calculate the mole fraction of solute and solvent in 3.0 mole solution of NaCl. Now the amount of solvent is not indicated, so we can say that 3 mole of NaCl actually dissolve in 1 liter of water, because the solution has to start from a unitary 1000 gram. So therefore the mole of our water now can be equals to mass over molar mass, which will be equals to 1000 over 18, which will give us 55 mole. So therefore the mole fraction of our water would be equals to 55 over the addition of both of them, which will be equals to 0.95, while the mole fraction of NaCl is equals to the mole of NaCl already over the addition of both of them also. The second thing we need to understand now is these categories of things. People do get confused while explaining them. What do we call vapor? Vapor is the gaseous state of a substance, like let's assume liquid. Now when you see steam coming out of a boiling water, it is called the water vapor. And you should know that the steam coming out, they are escaping. So therefore it is like an open container. Why vapor pressure? Vapor pressure, the difference between vapor and vapor pressure in most cases is that vapor happens in an open air space, while vapor pressure is in an enclosed container, which tells us that nobody is escaping. So the vapor pressure is the pressure exerted by a vapor in equilibrium with the liquid or solid phase at a particular given temperature. That is the two difference between the both of them. And this vapor pressure, we'll move on breaking it down better when we get to vaporization and condensation. Now, the partial vapor pressure. The partial vapor pressure is the pressure that is exerted. You can have a two gases mixing together in a particular closed container. Then it tells us that the partial vapor pressure is like the pressure of just one of them that it is exerting. I get I'm saying the pressure exerted by just a single component of the mixture of gases. That is to say, if you have hydrogen gas and oxygen gas in a container, the partial vapor pressure of oxygen is the pressure that the oxygen only would exert if it were to be the only gas in the container. Discussing vaporization and condensation. You see, when a liquid vaporizes in a closed container, gas molecule can never escape. So these gas phase, they used to move randomly. And you know that so far they can't escape. When they hit the wall of the container, they would likely bounce back. So they will be moving randomly about, and they will come back again to collide with the surface of that liquid part that has not developed into gases like that. So they called it the surface of the condensed phase. Now, in most cases, the collision will now result in the molecule going back into that condensed phase. And you see, when it now moves, that's the movement or the changing of the gas phase to liquid, we used to call it condensation. Now, when the rate of condensation is equal to the rate of vaporization, after it has moved into it, then it is at a certain position. That means that we meant neither the amount of the liquid nor the amount of the vapor are changing in that container anymore. The vapor is now said to be in what we call equilibrium with the liquid. And you have to note, oh, since I told you guys that in that process, it does not just only stay in one place, it has to move around. You can't call it a static equilibrium. It has to be called a dynamic equilibrium for the status of vaporization and condensation to be met. So the pressure that they exert by the vaporization or by the vapor, which is at equilibrium with that liquid in that closed container at a given temperature, we used to call the pressure which is exerted by that vapor, the vapor itself, a vapor pressure when it is in an enclosed container, or we say equilibrium vapor pressure. But in most cases they don't put dynamic in, sometimes just say equilibrium. So you have to note also that the area or the size do not usually affect the vapor pressure. It doesn't affect it anyhow big the container is, but just that it will take time. You know, the time it will require less when it is a small container for it to quickly move into equilibrium. But if it is a large container, it will take a little bit time also before it could move into equilibrium. So that is just one thing you need to understand under that. The next section is discussing about lowering of vapor pressure. And vapor pressure of pure liquid is what we have to consider first, which I had explained everything already. And we need to know something we call volatile liquids. What are volatile liquids? Examples of some volatile liquids are water, acetone, and the rest. And you see, I told you guys that a liquid in a closed container will establish an equilibrium with its vapor, right? And when that equilibrium is reached, the pressure exerted by that vapor, we are going to call it a vapor pressure. Do not forget that. Let's proceed. Let's assume that the vapor pressure of the pure solvent is PA0. That's like pure water. You see, a substance that does not have measurable vapor pressure, we used to call it non-volatile solute. Why the one that has a vapor pressure, we used to call it a volatile. That's volatile. Now, non-volatile solute are like glucose, sucrose, urea. And let's say that the vapor pressure of non-volatile solute now is equals to PB0. You know that will be equals to 0 because it does not exhibit a vapor pressure. Now, when we mix the solvent and the solute together, we are going to be given solution, which means that it is not just ordinary a pure solvent you are having anymore. And if they are being heated, let's just put it that way. You know, it gives us the vapor pressure, right? And we know that the partial vapor pressure now would be only that of water. That's the pure solvent there. As we all know that the vapor pressure for the solute is equals to 0. So the partial vapor pressure exerted by that solvent vapor is going to be equals to, let's say it is PA. Now, the main meaning of the lowering vapor pressure, this is how it goes. Now, when you now compare the vapor pressure of various solvents with those of the solution, that means when the solute and the solvent are mixed together, you will see that when you add a non-volatile solute to a solvent, the solution will reduce. That means it will lower the vapor pressure normal solvent, a pure solvent, vapor pressure would be greater than when you now add a particular solute to it. So that is what brought about lowering of vapor pressure. That is what they are trying to explain to us. There is a simple difference between lowering of vapor pressure and relative lowering of vapor pressure. The lowering of vapor pressure is like the change in the pressure, which is equals to the pressure of the pure solvent minus the partial pressure of the particular solution. While relative lowering of vapor pressure is equal to the change in the pressure over the pressure of the pure solvent. So let's take a particular example. Let's assume that we have a water of at 20 degrees Celsius. So the vapor pressure of the water is 170 torr. Let's say the temperature is constant, then we added glucose to the water. And we say that the vapor pressure of the water now over the solution is 14 torr. Find the change in the pressure and also the RLVP. The change in pressure would be equals to the vapor pressure of the pure solvent minus the partial pressure of the particular solution. And as you can see, you can also see that it said that the vapor pressure of water over the solution is 14 torr. So over the water means that you should know it is only the vapor pressure of water you can have in that solution, because that of the solute is negligible. So that will be 17 minus 14, which would be equals to 3 torr. And our relative lowering of vapor pressure would be equals to the change in the pressure, which is going to be 3 over the vapor pressure of the pure solvent, which is 17, and that will be equals to 0.2 torr. So we discussed about Rath law, and Rath law just states that the extent to which this non-volatile solute used to lower the vapor pressure, that's of the particular solution they are in, is proportional to the concentration. That means that the amount of particular molecule that you are putting into it will determines how lower the vapor pressure would actually be, which we've said already. So that is that partial pressure that is exerted by the vapor that's above the solution after they have mixed together, the one we would actually take is that of the solvent over the solute. So we call it partial pressure. So the partial pressure exerted by the solvent over the solute, that's Pa, is equal to the product of the mole fraction. That means that the amount of mole will determine, how much more it will lower it to, like we said, and also times the vapor pressure of the pure solvent. From the expression, we could say that what the partial pressure varies directly as the mole fraction of the solvent. And as we know, we have to neglect the solute, because the vapor pressure of the solute, or even the partial vapor pressure of the solute, is equal to 0, approximately 0. So it's useless. So from there now, we could say that what we know, we have a constant of proportionality, which is the pure solvent vapor pressure before it reacts with the solute, and that means Pa is equals to XA, then P naught A. Then if you guys could remember now, from this, that is our first equation of Raoult's law. That was what Raoult's law was trying to tell us. Now if you could remember, if you look at this very well, we could see that the mole fraction of A plus the mole fraction of B will be equals to A, looking at that formula that I broke down, and would be equals to 1. Then from there, we could say that the mole fraction of A would actually be equals to 1 minus what? The mole fraction of B, because we know the mole fraction of B will surely be even less than the mole fraction of A. So we call that equation 2. Now if you put equation 2 into equation 1, you'll be having your partial pressure to be equals to the vapor pressure of the pure solvent minus the vapor pressure of the pure solvent again times the mole fraction of B. And note, I just used the B to represent the solute. So you can use anything to represent your solute anytime you are being given a question. Just make sure you note your formula. Now from there, now if you are to make the mole fraction of the solute the subject of the formula, we are going to be having, our change in the pressure, which is the pressure of the solvent, the vapor pressure of the solvent minus the partial vapor pressure over the vapor pressure of the solvent. So we could easily say that what the mole fraction can easily be equals to change in the pressure or lowering of the vapor pressure over the pure vapor pressure of the solvent. Or we can say that the mole fraction is equals to the relative lowering of the vapor pressure. Do not forget from our expression from molality and mole fraction that mole fraction also can be equals to this. So we can say mole fraction of B is equals to the number of mole of B over the total mole, just like we said earlier in our previous class. Now, but if you look at this case now, we are talking about a dilution. So if it's talking about a diluted solution, the number of base, as we know, is the number of the solute we know of mole is very lower, very lower than the number of mole of A. So A constitutes it better. We can easily ignore the number of mole of the B, just like we say approximately equals to 0. So from there, and this thing, guys, you know that number of mole is equals to mass over molar mass, right? But at times they do call it weight, but weight is much more okay. You get what I'm saying? So some certain questions they will give you. So anyone you use, you are still on the same track. So the mole fraction of BA will be equals to NB over NA, which when we break NB, that is weight of B over molar mass of B divided by weight of A over molar mass of A. So you can break that down as what you can see. So we can easily say that what the relative lowering vapor pressure can be equals to NB over NA, or we say that the relative lowering vapor pressure also again can be equals to what the formula at which you can see. So they are interchangeable. You can change them anytime you want, and also it can be easier for you to solve questions with all these formula I had stated than just sticking to one point without not getting what you need. Let's take a look at a particular example. It says that the vapor pressure of pure benzene at a certain temperature is 0.85 bar. That's it, normal vapor pressure before it's mixed with solution. So after this particular non-volatile solid weighing is 0.5 gram, like I said, they can use weights, and if you use mass with it, you are still on the same right track. So it's added to 39.09 gram of benzene. So the vapor pressure of the solution is 0.845 bar. When they say solution, you should know that non-volatile cannot take anything. So that means that the partial vapor pressure is for that of what? Of still benzene, which is 0.845. So the question says, what is the molecular mass of the solid substance? That is of the non-volatile. Now let's move on with this. If you look at this question very well, you see there's something that is just only important in non-volatile, and that thing is just only their mole. That is what we do need most in most cases with a non-volatile. But if you look at this now, this is a little bit different. So let's check out the formula we can use for it out of the formula we stated in our previous class. So from the formula I gave you guys, the easiest one is using the relative lowering of vapor pressure equals to the weight of the non-volatile times the molecular mass of the volatile over the molar mass of the non-volatile times the weight of the volatile. So we are being given all of them, but we need to know the change. That's the lowering of the vapor pressure, which is just the normal pressure of the benzene before it's mixed with solvent, minus the partial vapor pressure. That's after it has mixed with the solvent, and everything are listed there. That will give us 0.005. Then from there we are only looking for the molecular mass of the non-volatile, which make it easier. So we cross multiply and do some 1 or 2 breaking. Our molecular mass of X would be equals to 170. So can you see how simple it is? Let's take a look at this second example. It says that glycerin is a non-volatile non-electrolyte with a density of 1.26 gram per milliliter at 25 degrees Celsius. Then it says calculate the vapor pressure at that 25 degrees Celsius of that solution. So since they're talking about the solution, that means they're looking for the partial pressure after they add 50 ml of glycerin and 500 ml of water, and they've given us the vapor pressure of the pure solvent at that 25 degrees Celsius, which is 23.8 torr. So this is very simple. What you just need to understand is that we need to get the mass, right? Or we say weight. Now from this question, you should know that since they are giving us density would be equals to what? Mass over the volume of the water. And they gave us the density, they gave us the volume of water. We can cross multiply from there to find the mass of the water and also the mass of the glycerin by using that formula. So let's move on to the solving. Since we are dealing with Raoult's law here, because we are looking for the partial pressure, if you have to use any other formula, it will be a little bit complicated. So we find the mass of glycerin and mass of water from the same formula. And from there now, we should know that what our pure solvent pressure is 23.8 torr. And to find the partial pressure, we need to find the mole fraction, which tells us finding the mole of water and also mole of what? Glycerin. So the mole of water would be equals to the mass over molar mass, which would be equals to 35 mole, and the mole of glycerin will be equals to the mass over molar mass, which would be equals to 0.685 mole. So from there, the mole fraction of A would be equals to 0.976. Do not forget. So we can find our partial pressure, which would be equals to SA plus times our P naught A, and that will be giving us 23.2 torr. Route law can be used for two or more volatile compound also. So you just follow the same law. Instead of we ignoring the other compound, we are going to accept it. So, and it involves doubting partial pressure. You know, doubting partial pressure. The partial pressure, I've explained everything already. So to find the total pressure, if you have been able to find the total pressure of two or more volatile compound, it's just like adding the partial pressure of A plus the partial pressure of B and relating it to Raoult's law. That would be the mole fraction of A times the pure solvent pressure plus the second mole fraction of B, then times the what solvent you are being given, or times the compound you are being given. So that is how to work that out when you are being given two or more volatile compound. So you can be given volatile compound which are two or more than two. This is how you are to do it if you have been asked to find the total pressure. Just add their partial pressures together. Let's take an example on that. It says a mixture of benzene and toluene containing 1 mole of benzene and 2 mole of toluene. So we've used the mole to find our mole fraction, which is being given to us already, and the vapor pressure of those substances are being given. So we are just to find the total pressure above in this solution. So we need to find the partial pressure because that is the one we have to add together. Now from the question now we can apply Raoult's and Dalton's law together to get whatever we need. And from there we know that the partial pressure of benzene would be equals to the mole fraction of benzene times the pure vapor pressure substance of benzene. The same thing goes to the toluene also. From there, as you can see, our answer for the total pressure will be equals to addition of both of them together, their partial pressure, which will give us this. Thank you. Please like and subscribe. Thank you so much. That is all under lowering of vapor pressure.